Thanks, Richard. Well, it's a real honor to join you, and to join you at the beginning of Caesar's year is particularly special for me because it's also Diwali today, Festival of Lights. So I hope to illuminate slightly this interesting topic that kind of tells the story of how, as a medical doctor, I ended up being asked to give talks on AI, and how did that exactly happen? I loved The Hobbit and Tolkien when I was a child. Obviously, you may know that The Hobbit is not the full title of the book. Actually, it's The Hobbit or There and Back Again. So I'm going to talk about my journey about taking concepts that started out being applied mathematics, then ended up being being labeled as AI, from concept to clinic, declaring success on that, and then more recently, then understanding, right, well, now we've got AI in the clinic, how do we bring that back into a laboratory setting to really innovate on the kind of AI that we want to build for the future, basically. So this is the boring stuff. These people give me money. Everything that I say is my own opinion, and I reserve the right to be highly opinionated. Thank you. So what I'm going to talk about is, how did a medic, a Cambridge medic, end up getting into AI? My experience in the middle crunch point of my career of crossing the valley of death as an academic doctor, where you're interested in concepts, you can see how you want to get them into your clinics and, to help patients, but there's this big step in the middle, and how do you actually make that happen? Then to talk through my journey of a particular project called OSAIRIS that was a lot of fun, and it was the first time we actually got to build an AI-powered medical device at the hospital at Addenbrooke's, and a little bit about that story, and then a little bit about my current projects, basically what I'm doing with the team at Microsoft, and also my current fund is the International Cancer Expert Corps, and what we're doing there with AI to really transform how radiation therapy might be accessed all around the world. Okay. So the story starts off in 1991 with this chap, who, is that going to work? Oh, yes. Horace Barlow, who was a professor in the neurophysiology department. This interesting device, which was an INMOS T800 transputer, it was the university's very first parallel computer, and you had to program it in a horrible language called Occam, and cats. And all three of these things led to my interest, basically, in working on what's now known as machine learning, neural networks, AI, that kind of thing. And so basically, Horace was a really interesting chap. At the time, we thought that the brain operated at a clock frequency comparable to a computer of about 0.5 megahertz. And when you consider now that your computer operates at how many ever gigahertz cycles kind of thing, he was convinced that the vision signal coming into our eyes was just too much information for the brain to be able to process in real time at 500 hertz. Too much. So he decided that there had to be dimension reduction mechanisms, and the information had to already start to be processed. And his idea was that it happened even in the retina, because there were simple neural networks available in the retina. And this built on the field, basically, very much of sort of very detailed experimental work, where you could rear cats from early on in their life to be grown up in an environment that contained either vertical stripes or horizontal stripes. And that sensory input would shape basically the organization of what's called V1, the primary visual cortex, where information from the eye is first received and gets layered out into a structure and then processed, basically. And so from some very elegant experiments at looking and measuring these particular signals from bars of light, so dark, light, dark, and then to taking electrical recordings from the brain, we could think about how columns of nerve cells in the brain would have to operate to encode this information, and how to understand that something was a bar of light, you would need some kind of cell that brought in information from these different columns. And these were, in the original papers from Hubel and Wiesel, 1963, they got a Nobel Prize for this, by the way. These were called simple cells, and then the complex cell was the integrator. It put all of this information together, basically. So I got to work on Horace's lab, doing an experiment of this kind, basically, and I used the parallel computer in order to generate fields of dots that you could then displace slightly and that human beings would still recognize it was the same pattern of dots, but they'd been rotated or shifted. And do this lots and lots of time and see what we could infer about the organization of nerves in the eye, basically, that might encode this pre-processing layer. Okay, and this just shows basically how very detailed anatomical dissection of V1, the primary visual cortex, produces a map of this network of nerves and how information basically flows in and is then started to be processed and feedback signals build up to actually start processing this information together. So we were interested in this from understanding and decoding how the brain was working, nothing else basically. And a week before my Part 2 exam, I read this paper in the library in neurophysiology. I realized it was quite interesting, so I read it and then I hid it away. I didn't tell anyone else on the course that it was there. What this paper said was that if you want to create this type of organizational structure between nerves so that they pass information back to the parent nerve, there are actually some experimental paradigms that show that this can happen and that the junction that allows an upstream nerve to speak to a downstream nerve can actually pass a photon backwards. Okay, and they elucidated the biochemical mechanism by which this is called, and this was called a back-propagating neural network. I read the paper, I wrote about it in my Part 2 tripos, I got a first, that meant I got a first in medicine. That put me on my track for the rest of my career as being some clever guy, all because of this paper. So I use this paper a huge amount, a huge debt of gratitude. I then forgot about that paper in 1991 as I went to the clinical part of my training, learning many thousands of facts that were not as intellectually stimulating as anything that I was doing there. Until about 2011, I had a chance to go and meet this chap who is Antonio Criminisi. Some of the people in the audience here know and play tennis with this guy, basically. And he's a computer vision researcher based at Microsoft. Now, he had been working on a project called Project Natal, which took the signal from two cameras pointing at different angles at an individual and could basically build a depth picture from these two 2D flat pictures. And from the depth picture, he would then start to build basically algorithms to parse out different parts of the anatomy. And why was he doing this? So that you could, it's Microsoft, of course, so you could play a video game. So Project Natal basically became part of Microsoft's $3 billion investment into the gaming industry to basically mean that you could play video games without playing video games, without having to pick up a controller. And I heard him talking about this, and I said, look, this is very great. You've got this eye that can examine the outer anatomical pose of the body. But honestly, we want you to turn your eye to the inside of the body and parse out interesting things, interesting features within the body. And that's why our project was called Inner Eye, in fact, because it was an eye trained on the inside of the body. Because I'm a neuro-oncologist, we started working with this condition. This is a glioblastoma, the most aggressive type of brain tumor that we commonly encounter. And its full name is glioblastoma multiforme, which means many shapes. And the reason is, you can probably see even from here, that there are different compartments to the tumor. There's the bit that's growing so quickly around the edge here that it's got a very rich blood supply, and it's dying off in the middle. So it's necrosed in the middle. And we can see the area that it's infiltrating into the surrounding brain before it actually turns into the tumorous mass. And we basically developed, as part of a global challenge at the time, a machine learning algorithm that could detect and mark out these different regions. It was a global challenge. There were about 70 labs competing, and we did the best. So we got the prize for that year, kind of thing. So that was great fun, basically, and started off a long collaboration with Antonio and his colleagues at Microsoft. And then he showed me this in 2012. Oh, I nearly fell off my chair. He said, Raj, there's this thing coming in computer vision. It's called deep learning, or a deep convolutional neural network. It is a structure by which you can take computational nerves and encode them together to allow information to flow in a way that the nerve structure can be trained by the data and only the data itself. But in order to make this work, which is modeled on the way that a real nerve works, we need to feed a signal back to the upper layer of nerves, something called backpropagation. And I thought, my goodness, I knew about backpropagation in 1991, but we were solving it with differential equations for 3 nerves on a piece of paper. He was solving it for 50 million computerized nerves, 50 times a second, using very high performance computing, basically, in order to be able to process images in this way and learn from the data effectively. And this is the basis of deep learning, deep convolutional neural networks, that was made famous by this paper of Ronneberger in 2015. And it's the reason why, in around about 2015, object recognition in your phones, number plate recognition in cars, even voice recognition. You know when you ring up the phone and it's a computer that you're speaking to, and it went from being lousy at picking up what you're asking for to actually being reasonably good? Well, this is the reason, basically. Deep learning then started to get implemented in different domains. And what it does, basically, is that it takes a medical image here, it breaks it down into small chunks, and it gradually learns the relationships between different dots in the image. It then takes that information and feeds it down to another layer, and gradually this information is put together and then reintegrated in a way so that you can learn what's called the semantic context, the meaning behind the relationship between the dots in the image, and then perform some kind of task. In our application, we were interested in what's called segmentation, so drawing around the anatomical structures in a scan. But the same technique can be applied, for example, to a classification problem or a prediction problem. You just basically modify the, output layer of the model depending on the task that you have. Okay? And so that's what we do now. Basically, in deep learning, all that deep learning does is to take a very, very complicated neural structure modeled on the brain. You feed in input images together with the answer of what you're looking for, okay? And then you allow that to move through the network in a way so that it can calculate what's called a loss function, which is the difference between what the computers guess at what this was and what the ground truth was, or the gold standard, basically. And what the computer does is that it has a go at classifying your data, it does its prediction, it works out its high score, and then basically it feeds back the information in that high score to adjust the connections between all of the layers in all of these computerized neurons that sit in a computer. And that's basically how it works. And that's how you train these deep learning models with lots and lots of data. I was having a lot of fun at this point. I got to the end of my clinician scientist fellowship, and I was realizing we were doing interesting stuff, but I really wanted to be able to move it to the clinic. I wasn't sure I was in the right place, and I thought I might have to go and move to industry. I was talking to a colleague that's just done an industry-based PhD on AI. So much so that I actually went to a training course in Phoenix in Arizona that was actually about learning how, as a doctor, to be a software development engineer. And so I got to visit the Grand Canyon, basically, and thought, well, that reminds me of the Valley of Death, basically. So. And what's been interesting has been my experience of actually early steps at crossing the Valley of Death. Because first I did it hand in hand with an industry partner who knew how to get to the other side, basically, and build a medical product. The first time I did it, I had been using very simple computational models, something akin to a cellular automaton here, effectively, to model how tumor cells spread through the brain. Do you remember that glioblastoma that I showed you? It turns out that that kind of code that I had was very good at modeling when we had got the edges of the segmentation of healthy anatomy wrong on a radiotherapy planning scan. And that the way to actually calculate how far wrong one of these what's called segmentations was compared to the correct answer in 3 dimensions was actually to do it iteratively. So I wrote an algorithm to do this, and I published it basically largely so I could cite it in myself in future research, and I produced a small code toolbox that I shared with the community. That was my motivation for doing it. At that time, the American Association of Medical Physicists realized that we in radiotherapy were doing all kinds of interesting things to image data to target tumors. This included bending and warping images so that we could lay them one on top of the other. For example, taking an MRI scan and mapping it onto a CT scan so that you could use biological information from the MRI to help plan the radiotherapy. And they thought, we should have standards for how we do this. We should make sure that if you're going to warp an image and then direct radiation into a patient as a result of that warped image, you should know what your errors are. You should know what your uncertainty is. So basically, my algorithm became very, very lucrative. And a company called Oncology Systems Limited in Shrewsbury, they rang me up and they said, yeah, Raj, we've read your algorithm. Do you mind if we incorporate it into our piece of software called IMSIB-QA, basically? And I said, I'll be delighted. That's fantastic. I didn't get any money for it because, of course, I'd already put the algorithm in the public domain. But what's interesting is that IMSIB-QA became the global leading software for quality assuring this type of very technical radiotherapy. So my algorithm directly helped thousands and thousands of patients, basically. And so it was picked up by physics, where I developed this, to say, could the university use it as an impact case assessment? So even though I didn't get any money for it, the impact case assessment was worth about £1 million to the university. But that was one of my first experiences, basically, of kind of crossing the valley of death. Then in 2016, something really interesting happened at Microsoft. And Antonio, that I showed before, he said, Raj, I've got a slightly wacky proposal for you. Would you like to join me in a startup? And I said, no. He said, hang on a minute. The startup is going to operate completely within Microsoft, within Microsoft's R&D budget. And we are going to take the algorithms that we built for that BRATS challenge, and we're going to turn it into a commercial grade product. I've got the clearance, I've got the budget, we're going to expand our team 20-fold, and we'd like you on board. I said, I'm in. And we got to do things like this, basically. This slightly caricatured mock-up was me testing out effectively our commercial grade code, and we just happened to be in the bunker with the radiotherapy machine to give it a bit of context, of course. I would never sit here and do that task in there, but anyway, but you get the idea. So InnerEye became a commercial venture, and we started to speak with all of the might of Microsoft to various clients, and I had a lot of fun. This is the world's largest healthcare informatics conference in Las Vegas. We went in 2015. Microsoft had an enormous stand there, and there's little old me and Antonio talking to, as it turns out, the Turkish health minister, who thought this was fantastic and said, when can I order 60 of them, one for each of my cancer hospitals that I'm thinking about? So it was a huge amount of fun. But then what I call the Ouroboros effect kicked in. Microsoft is a very large company, so risks proportionally are very big for a large company. And they realized that we were about to compete with giants like Siemens and Toshiba and GE, some of Microsoft's biggest customers themselves, okay? And they realized that it didn't necessarily make very good business sense to do that, particularly because Microsoft builds technologies. It's horizontal. It's not a healthcare provider, a vertical. So we decided at the end of all of that work to just open source, everything that we'd built into this framework effectively. Took out all of the data. No one could have any of the data that we used, but the actual tools basically put out there for the general benefit. And so that was really the point where I got to, where I thought seriously about investing in doing some work that gets across this step here, the valley of death, from something small that you develop within your lab in the university to actually having this point, level 7, a system demonstration in the real world. Because that's really hard. You know, you can write up your paper here and declare success if you're in a lab, but getting across here is difficult because you're not making any money until you get to this point, right? So then, in 2021, the government created NHSX as an entity to kind of promote sort of, digital innovation in the NHS. NHSX had an AI lab It had an AI skunkworks. It was full of nerds like me who really, really wanted to unleash AI for the benefit of patients. And there was money. So I applied for some, and I got some, basically. I got £500,000 from the government to build something called OSAIRIS. And what we did was, OSAIRIS stands for Open Source Artificial Intelligence Radiotherapy Image Segmentation. I do love a good acronym, I really do. And what it did was, it took the open source tools that Microsoft left behind at the end of Project IDRI, okay, and we brought them into the hospital. And so this is the problem that we're dealing with now. This is a radiotherapy treatment planning system for a patient that has a tumor that can spread through any part of the brain and spine, effectively. And so in order to give the radiotherapy treatment, we have to cover the whole of the brain and the spine from top to bottom. And that means there are an awful lot of healthy tissues that we need to mark out so that we can avoid them as best we can. And you can see at this particular level, you can see we've got the lungs, the heart, the breast tissue, the arms themselves, and there'll be hundreds and hundreds of structures that we need to mark out in 2D. This, for my colleague, before we built the AI, used to take her about 4 hours to complete, basically, before she even set about marking out the tumor target. So what we did, basically, was to use the tools that we'd built at Microsoft to take the data from the patient when they were having their scan for radiotherapy, send them to a device that de-identified them, encrypted the data, and sent them into the cloud. We were one of the first hospitals in the UK, basically, to connect up a cloud system specifically for running AI tools. We then ran the models, basically, in the cloud, and then it sent back the results, which is basically to mark out where all these healthy structures are. We started out with 2 tumor sites. Prostate cancer, because it's one of the commonest we deal with, it's about 1/3 of our workload, and head and neck cancer, because the anatomy between about here and here is so fantastically complex that for every patient with a head and neck cancer treatment, it takes about an hour and a half to mark up all those healthy structures. So one was high frequency, one was high input, basically, and then we decided to do those 2. And so what happened was, when the oncologist then sits down ready to start planning the treatment, all of the healthy structures are marked out. They can just work on the tumor. And so we were seeing 12, 13-fold acceleration in how long it took for your oncologist to actually prepare your radiation therapy plan. Then a very bright medical physicist would take that plan and work out how to actually get the radiotherapy machine to deliver it into a patient. And then at that point, you can go to one of our linear accelerators and actually have the treatment and hopefully be cured. So it was a heck of a ride doing all of this, because we got to do it properly without the pressure of being on the clock of a startup where every day is costing us money, and really think, how are we going to do this properly and test it to demonstrate it safely? So our clinical evaluation, even to this day, sets the bar as the best clinical evaluation of a software medical device that's been produced within NHS England. We produced a technical file to go forwards for UKCA marking, but the hospital said, we can't do that ourselves. We will not act as your legal manufacturer for a software device. We cannot have people ringing up Cambridge 245-151 and saying the AI is not working, and have a switchboard say, have you turned it off and turned it on again? Not happening, okay? So we had to identify a legal manufacturer who would then take it to market, because the hospital would do everything else but not act as the legal manufacturer. NICE basically did a medtech innovation briefing where they looked at the use of auto-segmentation tools in cancer care, and actually ours was included in the medtech innovation briefing alongside other commercial solutions. And then we've now been able to identify a legal manufacturer and move everything forwards, basically, in this space. But building a technical file within the hospital setting was a really nice thing to do. We got a very good understanding of how to build an AI-powered medical device within the hospital, and how to put in all of the tests that proved that it was safe and effective without the time constraints of being on the clock, on the dime, and trying to get a product out and start earning money. And that was a real privilege to be able to do that. So the kind of thing that we did was that we collected data on how the device was being used. Of course, everyone would do that. We then started to look basically not just at the accuracy of the device, but to think about basically the risks of how this tool would change the workflow, basically. I used to call it the Dr. Pepper question. What's the worst that could happen? So, and then we basically worked out a way of understanding how we could mitigate all of these risks and the manufacture of a novel AI solution. And so these are the sorts of things that we did. We did timings to actually see if the tool is meant to save time, does it save time? Okay, we measured accuracy. But these are the really interesting things that we did, something called a mystery shopping exercise, which came through from a European directive that are emerging on how to test AI and comparing it basically with other solutions for doing the same problem. So the mystery shopping, I won't go through other things, but the mystery shopping thing was really interesting. Okay, and it speaks to biases. What happens when you get used to the AI in your self-driving car or your phone, and you start to lose that repeated skill of doing a task yourself effectively? So what we did was to use a parallel system, not the clinical one. It would have been unethical to introduce deliberate errors into the clinical system. And we basically asked the clinicians to do a slightly different task. And we just then tried to see whether the clinicians would actually spot and fix deliberate errors in the AI. We had to make them deliberate because the AI in about 5,000 patient cases that we tried didn't really make enough errors to use the real AI errors as a part of the test kind of thing. And these are the two things that we were testing effectively, and they're not quite the same, all right? Automation bias is something specific to AI. Automation bias simply means there is an automated way for some piece of information to be processed. You've seen it a bit. You get to realize, yeah, by and large, it seems to behave quite well. You stop checking the output of the automation bias quite so well, effectively, the algorithm so well. So then you pick up automation bias. Anchoring bias is a slightly different thing, which is the first time you see a representation of the analysis of some data, whether it's from a human colleague or an AI, that sticks with you. An interesting example is a legal trick. You know those whiplash lawyers, terrible people that advertise on the TV? There's a trick that they do. So in court, they will say, how fast was the car traveling when it smashed into you? And the person says 25 miles per hour, okay? Whereas the other lawyer will say, well, how fast was the car traveling when it collided with you? And of course, the people listening in will remember the smashed into because that was the first time they thought about that concept. Hang on a minute, this car hit this person kind of thing. So that's anchoring bias, and it's fantastically difficult to mitigate against that in any kind of automation workflow with AI. So this is the sort of thing that we did. We would introduce errors into the system artificially where the spinal cord, you can see here in black here, we're looking at the side basically of the patient through the head and neck region. Spinal cord is here, this black structure protected by the bones of the vertebrae because it's so important. It's also the most sensitive structure to radiation. So it's the one we worry about the most when we're doing radiotherapy planning. So we would deliberately basically make it too small or too big or just right and see whether the clinicians could spot it. And these are the results basically. We did lots of tests like this and we gave it to the clinician consultant, basically, a head and neck oncologist, but also obviously in our workflow, because this is so important, a second person would check this output. So there'd always be two humans in the loop checking this effectively. And so what we're looking for basically is in the columns to see the nose, where one actor didn't spot it and did another actor spot it kind of thing. And there are some occasions where there are some errors that we put into the system where neither of the actors actually spotted it. We thought, gosh. So that was very interesting, and we published that. It's the first time to actually publish an analysis like that of when you take an AI and drop it into a clinic. What is the impact not on the AI, but on the human behavior kind of thing? And it meant that we could then basically, the way we mitigated it was to say, well, we would issue a training document with our AI to explain to people what is automation bias and anchoring bias so that they understood and could check themselves from time to time. The other interesting thing that we got to do basically was to ask people, well, when you use the AI, did you take the AI's output and use it exactly as it was without changing anything? Did you take the AI's output and tweak it a little bit to your liking, but still use it? Or was it so bad that you just got rid of it and did the whole thing from scratch yourself? Okay, so that's the green, the blue, and the red bars, okay? What you can see basically is that this is OSAIRIS and this is its performance. So most people were saying you could take the output and use it exactly as it was. A small group of people were saying that you would, a modest group of people were saying that you would have to alter it a little bit, but still useful. And then just a very small number of times when you said, no, the output's so bad that I wouldn't use it. I deleted it and started again. These are two comparator systems, basically, that are commercial systems, and we perform slightly better than that. But this is interesting. This is our most senior head and neck oncologist. This prostate oncologist, basically. And what you can see is that even though this is our most senior oncologist, about a quarter of the time, the people actually reviewing this in this task felt that her outputs were not good enough and they delete them and do it themselves, which I thought was quite interesting. And it tells us that the difference between the human and the AI is less than the difference between a human expert and a human expert. And that's, I think, an important principle, that once an AI becomes accurate at a task, further accuracy, of course, is nice, but it's then its consistency. It performs the same on a Monday morning as a Friday evening. It doesn't need a glass of wine to get it over the line for that last case, okay? It's just very, very consistent. And interestingly, in our user stories, that's one of the things that came back. They said, look, it may or not always get it right, but I know what it's going to do effectively. So then we started looking for people to kind of manufacture this type of tool. And I got to visit one of our collaborators, a company called BrainLab, and they produced this space as a vision of the future as to how radiation oncologists and surgeons and radiologists who read the scans were going to interact. And it's a bit like, looks like the bridge of enterprise here. So these are all the individual stations where each of the specialists would work. And you have this joint space where you can visualize the data together in an augmented reality framework. I thought that's pretty cool. Well, it turns out our legal manufacturer that we've identified is a company based in Germany and Poland called Apokla. They basically produce visualizations of medical images to help surgeons so that they can look at the patient's scan whilst scrubbed up and interact with the scan and then go back and go, all right, yeah, I need to know what I need to do next. But there's no AI in their system. There's no interaction with the oncologist or anyone else in the system. So by bringing our two technologies together, I can have a dialogue with a surgeon who's on the other side of the world and say, yeah, you know Mrs. Jones that you operated on with her meningioma or whatever it is, I've got a planned post-operative radiotherapy. Could you just show me exactly the bit that you were worried about where you think the tumor may not have been completely removed? And they just paint it on. The AI marks up all the healthy structures. I take that brush stroke from the surgeon, use that to plan the radiotherapy, and off we go. So that could really be paradigm changing, because at the moment, certainly in the NHS, our respective times are too valuable for us to come together and have a group powwow at the time that we're actually thinking about doing the radiotherapy planning. So watch this space. So having gone from that concept to the clinic, now it's 2025, and I'm interested in an interesting set of problems where we know AI is in the clinic and it's here to stay, but how can we actually take what we've learned in the clinic and build better AIs that do what we actually want to do? And the areas that I'm interested in is what's called a multimodal fusion problem. How do I build an AI that's just as good at looking as my images, but also can read words, medical notes, textbooks, for example? And how can we build what's called a foundation model? And a foundation model basically is a multi-purpose AI. So everything I've showed you so far have been very, very hand-tuned AIs. They've been built and trained to do one thing and one thing only. But can we start to build models within a certain area, like head and neck cancer, that can solve different types of problems, but using one common set of knowledge and data? And then generative AI, that's the other area that we've been looking at. So just to show you some of the examples, this is working with Microsoft, and this is a tool called Myra 2. It is a foundation model that's very good at reading chest x-rays. It's been showed about 40,000 chest x-rays. It's read every radiology textbook relating to chest x-rays that we can find. And what it can do, basically, is that it can look at the x-ray. Sorry, I've run out of juice of the pointer. And it can look at the radiologist's report, and it can work out whether there's something missing from that report. And it can then point out and say, hey, I think you might have just not noticed this particular nodule here that might be hidden in the shadow of the heart, kind of thing. Great fun to be able to build tools like this that now actually going out and helping very tired radiologists, because radiology is a hugely expanding field in medicine, kind of thing. And having these assistive tools that are looking over your shoulder is really how radiologists want to work. What's interesting is we took that model and we said, okay, well, that's great. Is it only going to work in English? Will it only work for radiologists that report in English? So we then did an adaptation of that foundation model where we gave it Spanish radiology reports. And guess what? We managed to train it, basically, so that it's equally good and it transfers insights that it learnt from English, American, admittedly, radiology reports, to Spanish ones. So we made it multilingual. But not only that, we then took the model and we put it into something akin to a functional MRI scanner. If you've ever heard of this technology, a functional MRI scanner is a way of looking at which parts of the brain become active when you're doing a task by imaging very small changes in the blood flow. And we infer that if there's more blood going to that part of the brain, that's the part that's working on a task, basically. And so you can give people poems to read or complex motor tasks, and you work out for a patient where in the brain do those tasks happen, and that helps the surgeon to know where they can operate and where they can't. Because actually, although our brains have the same overall structure, they are a bit plastic, and the part of the brain that you use to speak might be slightly different from the person next door to you, kind of thing, even if you're both left-handed. We built the equivalent of a functional MRI scanner for large AI models. So you can put large AI models into this scanner, and you can do what's called activation mapping. So you can give it a task, and you can then identify in yellow the parts of the image that it's paying attention to when it's actually being given this information to process. And what we can then do is to actually see that, for example, these things match up. So when the computer is looking at the clavicles or the collarbones, is it really paying attention to the right part of the image, kind of thing? And that really changes the way in which we can integrate an imaging model and bring it together with other tasks effectively. That was one project I did. The next thing was really daft. I sit there in this thing called a MDT, or a tumor board if you're in the US, where a patient that's newly diagnosed with cancer is discussed. And there'll be a surgeon, an oncologist, a radiologist, a pathologist, huge amounts of expertise, and we'll discuss 50, 60 patients at a time kind of thing. But we're so busy now, we've got about 90 seconds to discuss each patient, basically, and decide on what is the diagnosis, what is the stage of the cancer, what other things about this patient do I need to worry about, and then what is the optimum treatment for the patient. So we thought, surely an AI can help with this. And it can. We built something called Cancer Guide, and what it did, basically, was we fed it the American National Cancer Network's guidance for the treatment of lung cancer. And we then used a type of large language model to turn that into computer-readable code. So that's this JSON decision tree, basically, using something called RAG, or Retrieval Augmented Generation. We then gave a very complex large language model the ability to read those guidance in a computer-friendly format. We turned it into what's called a decision tree. We then took referral information into a lung cancer MDT from an American clinic, and we had structured information with all of those bits of information that the model might need. But we also had just the plain referral letter written in plain text that might be incomplete or contain mistakes, basically. And we said to the model, read in these letters, take the information that you've got from the guidance, try and work out where the patient is on their lung cancer journey from the information in the letter, and predict what the next treatment should be. We also got some oncology trainees in the US to read the letters. They're supposed to know the guidance, and see if they could predict what the next treatment option should be. And we did a head-to-head AI versus human evaluation. And what's really interesting is basically this graph shows where mistakes were made, okay? And the blue mistakes are made by the model, and the orange mistakes are made by the humans. You can see in certain parts of the guidance, the model made far fewer mistakes than the humans did in correctly working out this is what the patient should be treated with. But then there were other areas where the human intuition, effectively, the ability to fill in some missing information, actually meant that they didn't make any mistakes and the model made some mistakes. So it's intriguing. It's not going to change how we run MDTs and, at the moment, but it's a very interesting kind of take, effectively, that we can take a large language model like GPT-5 and we can start to give it the ability to learn the gestalt, the underlying understanding of an oncologist who's been looking after lung cancer for 20 years or so. And then finally in this section, this is the work of Doris, one of my own postdocs. She specializes in using information theory to understand how machine learning models work. And what she said is that all the time in cancer research, people are building these fantastically complex models to then make classifications or predictions on research data. The problem is, when the model gets it wrong, it doesn't understand the difference between a small mistake and a massive mistake. So can we train the model in a way, I don't know why, just see if it's working again, so that it can learn to self-organize its predictions so that it understands that there's a big difference between finding that there's nothing wrong with this image at all versus these various entities. And so, for example, a slightly enlarged heart and a little bit of fluid around near the heart, a pleural effusion, a mistake between those two is a minor mistake, but a mistake between any of the three overall categories, that's a bigger mistake, basically. And we've been able to build ways to train machine learning models so that it can work out these rules for itself from the data, effectively. And then finally, we see a lot of kind of information about how images can be generated, the deep fakes, these fake things of Barack Obama saying things that he never said kind of thing. So we've been able to do this kind of work to synthesize images that might be clinically helpful. This is a standard MRI scan from a patient, and these color maps show the connections in the different parts of the brain of the patient. It turns out these connection maps between the different parts of the brain, they're very much the same between humans. They're actually the same between humans and monkeys. So if we fed a machine learning algorithm with a large amount of standard MRI scans and these connection scans, then it starts to be able to synthesize a prediction of the connection pathways in your brain from just a standard MRI scan. It's not good enough to study things like multiple sclerosis or Parkinson's disease, diseases of the brain. But it is good enough for a surgeon to speak with a patient and say, look, if you want me to operate here, this is how this part of your brain connects with other areas, and therefore these are the problems you're likely to encounter if we go ahead with this type of surgery, effectively. Final bit. So it's been very interesting to kind of build out these technologies. And most of what I've built basically has worked within radiotherapy. It's had impact within the UK. But I got to join recently a very ambitious project run by a US not-for-profit called the International Cancer Expert Corps. And the project is called STELLA. And it's based basically at CERN. This is the image from one of the collaboration areas that I have at CERN. And you can see basically the Atlas detector on the wall here. And we've got people from all around the world, including representatives from the African nations who are working on this project together. STELLA is designing a smart radiotherapy machine specifically for use in Africa and low and middle income countries, because Africa is hugely behind in its availability of radiotherapy machines to cure patients with cancer, basically. And you can see, in the US, for example, there is one radiotherapy machine per 100,000 people, whereas in Africa, it's one per 3.5 million people. And because because infectious diseases are starting to plateau and people are living long enough to get cancer in Africa, by 2030, there's going to be 1.4 million new cases of cancer. And we would need 400 additional radiotherapy machines in Africa to be able to keep up with that demand by 2030. So it needs new thinking in order to get there. And that's what the group does, basically. The other problem that they have in Africa is supply chains are long. And the kind of engineers that sit in our hospital waiting to fix a radiotherapy machine and get it back into use, because we've got 8 of them in our hospital, they will be thousands of miles away in many parts of Africa. Now, in Europe, when a machine breaks down, in a year, an average radiotherapy machine would be in total just under 4 days of downtime. It would be working the rest of the time. But you can see here that in some African countries, there were some areas where they had 40 weeks of downtime. Basically, that was in Madagascar. They bought a new machine. It broke very soon after they got it. And the supply chains are so long that it just took them ages to get the money together in order to be able to fix it. So we have this concept for a different design of a radiotherapy machine, basically, that we've been working on for some time, that it's just mechanically simpler, it's more robust, it's more tolerant to variations in temperature, in the electrical power stability that you get in Africa, kind of thing. And I was brought on board, basically, to power the AI behind this machine. And the kind of AI that we're going to build, there's going to be 3 different things. The first AI is because in Africa, patients wait a long time to even get to a radiotherapy machine. They often wait so long that they're diagnosed with a curable cancer, but by the time they get to the radiotherapy machine, it's incurable. So AI number 1 will take all of the information from when the patient was diagnosed, an X-ray, a scan, a report, and it will try and intelligently design a treatment plan for that patient before they even get to the cancer center. That's why I was interested in multimodal AI, interested in AI that could take information from an image and a text together and start to predict what the radiotherapy requirements might be for that patient. The second is that where Africa does get new radiotherapy machines, they don't use them to the best of their ability. They don't treat lesions precisely because they don't trust their own expertise to be able to do it. So what we will do, basically, we started working on this layer already, is building a large knowledge repository from centers all around the world who've got lots of experience of treating tumors in different locations in different parts of the body, using the same kind of technology that the African radiotherapy machines will get. And the idea here is that when the patient arrives, you take your prediction, you plug it into the knowledge system, and you get back some suggestions actually about how are we actually going to do the radiotherapy treatment. And then the third AI, which is really quite interesting, and we've got a PhD student working on this in Oxford, we're using a type of AI that was originally built for making predictions in the financial markets, something called a variational autoencoder. And we're using it to read the telemetry data in existing commercial radiotherapy machines. And basically, this algorithm now operates with a 90% level of accuracy, where it's reading the signals that the machine's sending to its different parts and saying, I think if you don't do something, there's a 90% chance that later today we're going to get an error. And the idea behind this is that if we can extend this, maintain that performance, but allow it to do the prediction further into the future, that we can actually get it to predict when a machine is going to fail, so that you can take it offline and fix it, rather than it failing completely and having dozens of patients arrive who then can't be treated effectively. So I'm now this kind of strange middle-aged medic who gets to talk about AI and also treat in the oncology department. And life is an awful lot of fun for me. I'm very, very happy. But I think, in terms of how I got here, particularly for the younger members in the audience, I'm definitely a geek, and I really embrace my inner geek. And that stuff that I was interested all the way at the beginning of my career actually then came back and had a tremendous influence of where I ended up, kind of thing. I do think you have to make your own luck, whether you're a medical student or in any other area. I think that boldness and that Cambridge effect of coming to meetings like this and speaking to people outside of your domain and going, that sounds interesting, can we organise a follow-up to discuss that in a little bit more detail, really pays dividends, because this was a Cambridge phenomenon. Chance encounters, multiple occasions, multiple different schools and departments in the university, giving me the opportunity to build a common language and a common understanding with a computer vision expert or an engineer or a computer scientist kind of thing. Choose your industry partners wisely. I think that if you're going to work in industry, you should go in when you're bold and full of ideas and have got domain knowledge and understanding, and you should get out when things are getting a bit soft and uncomfortable for you, okay? Because that's the time basically to start moving on and making some real impact. And then specifically, if you are interested in AI, in medicine, that comes to this thing, software as a medical device, which is a difficult thing to get right at the end of the technology readiness levels and get all the way out to market. But there are some things that you can do. And the main thing is, the things that you work out, write them down, okay? Contemporary notes have been so valuable to me later on in their career, because when that thing becomes a medical device, your ability to encode design choices basically justifies years of thinking. Why did I choose to do it this way? Well, I did look at all of the other ways of doing it, and I ended up choosing to do it this way because ... And you give that to the regulator and they go, fair enough, yep, that makes sense. And then the other thing I would say, and this bears on my experience, is that patenting software is really, really hard, okay? It's very easy to take the concept behind a software or an algorithm and just change it very, very slightly and go, oh yeah, this is something completely new. It's got nothing to do with, that whiz-bang algorithm kind of thing. And my experience has been, particularly for software as medical device, that actually writing your papers and getting it out there early is the thing that's kind of protected me. You saw that example with OSL, right? Well, basically their product went out and they had a challenge to their software, basically, to say that that particular aspect had already been designed by somebody else. They contacted me and they said, look, IMSIM-QA has been a threat from a competitor saying that we didn't invent mean distance to conformity algorithm. And I said, that's fine, just send them the paper, because the date of the paper predates when they did their filing, right? And that was the way, basically. So it actually solved it for the company. My paper basically was worth more to them than the patent, effectively. And I do love this quote, that in theory, there's no difference between theory and practice, but in practice there is. And I'm very much the kind of, learn by doing and, try and give things a go, basically. So I'll end there, and we're doing for time, a little bit over. Lots of people to thank. Here are some of the key people on the journey, and just very happy to answer questions. Thanks very much.
That was wonderful. We learned so much, very inspiring. You'll be happy to take some questions?
Of course, yes.
Right.
Yeah.
Can I make a plug for Archive? I'm glad to see you've just put your stuff on Archive. We put some stuff on Archive. It circumvents all this refereeing rubbish, doesn't it? I strongly recommend it, and people read it these days.
Yes, yeah.
They do, right. Okay, real question, right.
I speak as a customer of Addenbrooke's radiotherapy department in very recent times, so it's a bit biased towards me, this question, but two things. One is, did I benefit from AI? My cancer was on my vocal cords, so I had an A4 for that. And also, does it happen during treatment that the actual tumour changes shape? And can the machine cope with that? And is it an AI problem, or is it some other issue when you're trying to compensate for that?
Yeah, good points. So the answer to the first question is probably yes, because as OSAIRIS does, as I mentioned, work in the head and neck region, it will have not had the responsibility of defining the target for you, but just the rest of the anatomy, and your consultant will have done the actual targeting, so rest assured for that. And the second thing is what we call adaptive radiotherapy. So if a tumor shrinks, can you change the radiotherapy plan to make it either safer or even more effective by giving extra dose? And adaptive radiotherapy is a privilege of Western clinics. So we have workflows with AIs, and I could talk about I've got other work on that kind of thing, how we use that. But in Africa, adaptive radiotherapy is so far away from reality, they say, we don't want to know about this. Can you just help us make a radiotherapy plan that's right for the patient? So in the STELLA project, interestingly, we have deliberately not focused on exactly what you describe as adaptive radiotherapy because that's tomorrow's problem. That's a V2 problem, effectively.
Great talk. I really enjoyed it. I have a question that's a little bit philosophical. I was wondering, how do you think the advances in AI is going to affect the training of next generation of medical doctors? And do you foresee that there might be a case that some future doctors, for example, who would naturally gravitate toward radiotherapy or pathology, for example, now be scared that the AI is going to replace them? And what kind of training they can get to actually be still sort of useful and sort of productive in this future?
Understood, yeah. I think that training needs to respond to the influence of AI in medicine. And the main thing, I think, is that you need to develop the understanding of how these things are built, fundamentally how they work, and how you can evaluate them and make them safe. And so we need to teach data science and machine learning as core curriculum in the medical school. And I'm pushing very hard to do that. This week I got to teach on the university's first masters in healthcare data science. And that was 7 years of work, but it's starting now. In terms of what it does to actual jobs, I'm less worried about that. If you take the performance of GPT-5 at multiple choice questions, it can pass most American, even Japanese entrance examination boards for text-based multiple choice questions. Its performance will be around about 88–90%. Take a question that has an element to do with an image and some text. GPT-5's performance on these exams falls to about 12%. We do not have enough generalist AI tools that have the transferable knowledge, basically, to act as a serious disruption, an existential disruption to medical areas. So I think what will happen is they are interesting technologies. We will absorb them as we do with many things that have changed the way that we do medicine, but we'll still be here, at least for another 10, 15 years, I think.
So that business of the point at which the machine takes over completely because it can do everything better than the human is not imminent. I mean, it's quite interesting to note that your examples of tracing out which bits you didn't want radiation on, the arbiter in the end was a human being.
Indeed, yeah.
And that's not going to change any time soon.
It's very interesting. If you have time, there's a chap called Pranav Rajpakar from Harvard, who is a world expert in generalist AI for healthcare applications. If you read any of his papers, he writes for a lay audience, and they're beautifully written. But he did a very, very simple thing. He said, let's put an AI first into the system of reading a mammogram from a lady with suspected breast cancer. Let's follow up that AI with a human. In the first example, the human is an expert. In the second example, the human is a trainee. Okay? AI first, human second. The AI degrades the expert's output because it degrades his confidence in his own trained and expertise opinion. It enhances the trainee's output because, of course, they just not have the same number of observations as the AI does. So there's a lot of work in kind of understanding how we use these things best together that we're gradually working out. So, yeah.
So fascinating talk. I was interested in your fault prediction thread in the final part. I mean, traditionally that can be, it's always been the sort of the dream, but actually getting enough data to characterize the faults can be quite tricky. So do you have a sense of how much data you're going to need to make that successful?
Yeah.
In terms of things going wrong, but, do you need to see those first, I suppose, is the point.
It's a very good point. We work with the data science team from Rolls-Royce, who are based in Rugby, and they get telemetry data from every jet engine in the sky every 7 seconds. They only use 11 sensors, which is quite interesting. And for a long time, they were saying, we don't even need to use machine learning. We can just use regression models or other things like this. So we've used a simple form of machine learning to start with, a variational autoencoder, and about 4 months of data from a couple of commercial linear accelerators was enough to give us that performance. And it's good, 90% is good, but that also means that 10% of the time is telling you to shut down the machine when you don't need to. So it's nowhere near the clinic. We're then moving to a transformer model, basically, that starts to think of these codes as language that it doesn't understand and try and decode the language. For that, we think we're going to need about an order of magnitude more data. So we're trying to build that effectively. And I think it's an important thing, particularly in healthcare. Often the data you can get is the data you can get. It's unlike in finance or fintech or other examples where you can just go out and get a lot of data. So it's very important to match the algorithm that you're using with the volume of data that you get. Yeah.
And then finally, if I may, then I guess that data then becomes valuable in terms of the design time loop of can you make better machines in the future? Is that kind of on the agenda as well?
That's right. Well, that's been one of the lovely things about working on the STELLA project is at the moment we are using the data from commercial systems. We don't even have access to the underlying data model. So that variation in autoencoder is getting 90% accuracy without knowing the data model for those codes. But of course, when we build the machine, then we're going to be able to know that, design which sensors we want to put into the machine, having learned what's helpful for the variation autoencoder. We're also going to use open standards. So CAN bus, the thing that's in your car since 2012 that allows all the electronic systems. Now when the AAA or the RIC arrive, they no longer look under the hood, they plug in their computer and it tells you what's wrong with the car. So STELLA's going to be built on an extension of CAN bus because the whole thing will be open. And in that way, we hope that we can really facilitate basically the whole community to do these predictions in the future.
Thank you.
Can I just pick up that we have one question online. How many repetitions of feeding the algorithm did you have to do in order to make it considered accurate? It's probably heading back to an earlier
That's
question.
true. Yeah, so for example, the ones that we built in OSAIRIS, we have about 250 head and neck data sets from patients from our department with the ground truth. And for the prostate, it's around about 200. And that's quite impressive when you think that the model the model underlying it has about 50 million hyperparameters to train. But I think there's a little trick when you work with medical images. So of course it's 200 patients, but then each image is millions and millions of little points of data. And I think that really helps kind of thing. When you're dealing with other data sets, the input data is not quite as rich. So you may need more data.
Raj, that was a fantastic talk. Thank you very much. When you stopped the internal work in Microsoft and moved into the hospital environment, you might have said it, but I might have missed it. What do you think was the key thing that allowed you to, that caused people to allow you to start doing that work? Because you're obviously very busy and stretched for cash as well, and these things take money, I presume. So what do you think made your project stand out?
Well, having £500,000 to play with and give money to people to say, if I give you this, can you do this? That certainly helped. But more seriously, I think for me, this was the principle that I mentioned at the end about being the person that speaks the common language. That really helped me. Because when I went in 2021 to the hospital had just installed its own cloud system in 2020, right? I knew how to speak to the cloud solution architects. We did this on the back of me working at Microsoft for the previous 5 years. So I knew the technology in and out from the code basis because I've been part of the development team that actually put it together before it then got open sourced and handed to the hospital. And for me, that's the real thing, is take your domain expertise and become part of the glue, the common language, become the person that allows you to interface between the groups of people that are not talking, and that's why your thing is not moving forwards. This is particularly true of hospitals, sadly, but I'm sure there are other domains where the same thing happens.
Okay, thank you. That's very interesting. I had a similar experience when I was working of being able to talk two different technical language has made a world of difference.
Yeah.
I think we might transfer over to the bar shortly.
Very good.
Oh, we have one last question. Right. Sorry.
Okay, quick question. If this AI was, it made a mistake, who would be at fault?
Very good point. Yes. So who's responsible when the AI goes wrong? I think ultimately what we understand in oncology and radiology, these are the areas where AI is moving further fastest in healthcare, that ultimately a clinician has to take responsibility for the AI. But there is an understanding that there is some level of sharing of that responsibility effectively. And particularly if the fault is due to some underlying behavior of the overall solution and the code, then that then moves forwards to the responsibility of the manufacturer. Whereas if the responsibility is in how was that information interpreted and was it used within the scope of intended use effectively? So in other words, did you take an adult AI tool and apply it to a child when that was never the intention kind of thing, sits within clinical risk. So I think what's quite nice is that we're now understanding that you have device risk, you have information risk, you have clinical risk, and the right structures are being built in order to do these things. We also, amazingly, in Addenbrooke's, have just installed our first AI deployment platform called Newton's Tree. It is the AI that watches the AIs. And basically, all of the hospital's AIs get deployed into this platform, and it is continuously monitoring the output and running little test experiments on each one and making sure that the model is actually doing what it says on the tin effectively. So, you're right, of course, but we are fortunately in medicine working these things out at the same time that we're actually deploying, I guess, because people are aware the AI is coming into a healthcare issue, so we should be a bit more cautious, which is a nice thing. So.
Thank you.
Okay, well, thank you very much, Raj. That was a wonderful talk. You make it all sound very easy. I suspect you might be quite good at it. Thank you very much indeed.
It's a pleasure. Yeah.